Thank you all for joining us for this week's Power Hour session from Critical Environment Technologies, doing the fundamentals of gas detection and hopefully answering some questions about how the systems work, the components of the system, wiring, how they can be integrated to control your fans. And parking garages are one of the more common applications we see. And Jeff, I know you're going to go through that and a few other applications that our engineers and contractors might see. So as always, we have Scott and Nick from our engineering support team here at Dorse. Blake is out of our Spokane office. I believe he's at NASHRE meeting today. So we're always here to support everything you need from any of our fans. The gas detection you'll learn about today. Our housekeeping rules, please put all your questions in the chat. We will do our best to moderate and interrupt Jeff if we need to, but most likely we'll hold off to the end. This is being recorded and I'll get it posted to our YouTube channel as timely as I can for referencing. If anything you see here today you want to learn more about with your team, Jeff is happy to come to a lunch and learn or a webinar or anything you need, just the specifics to your team, go over any specific projects you might have. All right, with that, Jeff, I'm going to hand it off and I'll shut up for hopefully 45 minutes and let you run with this.
Great. Thanks a lot, Chris. Really appreciate the introduction there. And we at Critical Environment Technologies are very happy to have fairly recently partnered with Dorse in Seattle, and we've historically in our business tended to partner with a major fan manufacturer in every market, and we do partner with a lot of the green heck manufacturers reps, as well as obviously fans and gas detection go very, very well together. So very happy to be partnering with Dorse here. With that, let me get into the presentation here. What we're going to be talking about today is the fundamentals of gas detection. And Chris mentioned to me that there will be a number of engineers on the call here. This is actually a presentation that we give to our engineers. And this is an accredited course for PDH credits. It tries not to get too product specific. We try to make our presentations to engineers product agnostic a little bit, of course, with the hope that the engineers are going to take a liking to our product and specify us and then reach out to Dorse for further information. So today, of course, we will get into a little bit of the product throughout the presentation as well. So this is our agenda here. We're going to talk a little bit why we monitor gas in the first place. Seems obvious probably to most, but there's some things that we want to touch on there. We're going to talk about the gas sensors themselves, right? We're going to talk a little bit about the technology of the gas sensors. What does that look like? This is a gas sensor right here, a little gas sensor. We'll talk a little bit about that. We're going to talk a little bit about how the system works. How do these sensor transmitters, these gas sensors, how do they interface with the rest of the building, with the fans, with the building automation system, with the DDC system? Then we're going to talk a little bit about some specification considerations. What are some of the things that we need to think about, we need to consider when specifying a gas detection system in the various different applications that we get involved with? And then applications and solutions. There's probably 25 applications, and we could spend an entire additional hour or two taking a deep dive into all of those specific applications. We're not going to have time for that today. Suffice to say that when it comes to applications, the most common application that we get involved with, as Chris mentioned, is vehicle exhaust. Okay. Now, vehicle exhaust, that can come in a number of different forms. The most common one would be, of course, parking garages, which is a big portion of that vehicle exhaust segment that we work in. However, there's a lot of other applications that we get involved with vehicle exhaust, such as distribution warehouses, a really big application for us. You've got places like Amazon where you've got vehicles entering inside that building envelope. Then you've got police stations, fire halls, ambulance bays. All of these applications where you've got vehicles entering inside a building envelope. And we're certainly going to talk a little bit about that. The second largest application that we get involved with, and actually the application that's growing at a very high rate, is refrigerants. With the recent changes to A2L refrigerants, there's a number of things that we had to do from a gas detection standpoint, and we'll talk a little bit about that as well. And then towards the end, I'll pull up our website just briefly and go into the resources that our team has prepared for our engineering partners as well as our dealer partners. And I think you'll find some of that very, very interesting and very useful, particularly for those engineers in the audience, but also for the dealers that want to find a lot more information about our products and services that we offer. So with that, let's get into it. Let's talk about why we monitor gas in the first place. So here's the main couple of reasons why we monitor gas. Of course, the protection of lives. And what we're talking about here with the protection of lives are those toxic gases, right? Those toxic gases that, if ingested, breathed in to the body, can cause serious harm to the body, up to and including death. Those are those toxic gases. And then you've got the protection of property, which is referring to those combustible gases, right? Those combustible gases where if you have a source of ignition, if you have a spark, if you have a source of ignition and you've got a leak of a gas that can pool in a certain area in a building envelope, you've got the potential for a flash fire within that facility, which is why we want to monitor those gases. And when it comes to protection of property and those combustible gases, we really need to think about the molecular weight of that gas, right? Is this a lighter than air gas like hydrogen and methane, where we need to put that sensor up towards the ceiling? Or is it a heavier than air gas like propane or refrigerants that we need to put that sensor down below, close to the floor of the facility, right? And in both of these cases, whether we're talking about those toxic gases or the combustible gases, we're really introducing demand control ventilation. We're only turning on those fans when required, when we get a certain ppm level that we need to clear out that air and bring in new clean air into that facility. Okay, if you think about this technology, right, these gas sensors, these transmitters, they've only been around for, let's say, 30, 35 years. But there were, in fact, underground parking garages and above ground enclosed parking garages and other applications where there were vehicles entering inside of building envelopes. Well, how did the industry sort of deal with that? Well, a couple of ways. Number one would be to run those exhaust fans on a schedule. Or number two, run those exhaust fans 24/7, right? But if we think about that, and that leads us into the protection of the environment here, if we think about running those fans 24/7, you've got a number of considerations there. You've got the energy consumption of running those fans 24/7. You've got the wear and tear on those fans. And then you've got any makeup air considerations where it could, A, take a lot of energy, and B, cost a lot of money to run those fans 24/7. So again, gas detection is a way to, yes, protect lives and protect property, but also protection of the environment, saving energy, saving money by only running those fans when required, when that ppm level or that lower explosive level gets up to a point where we need to clear out that air. Okay. There are a number of regulatory authorities that we in the gas detection industry focus on and look at when considering and designing our gas detection systems. And many of you, or most of you, if not all of you, will recognize at least one or two of these organizations on the screen here. You'll see there you've got NIOSH, the National Institute for Occupational Safety and Health. We'll look at that one in a little bit. And then the lower left there, you've got the American Conference of Governmental and Industrial Hygienists that talk about threshold values, about exposure to gases, right? So when it comes to the NIOSH, if you go into your search engine or ChatGPT, whatever you want to do to search, and you enter a NIOSH Pocket Guide to Chemical Hazards, you will get a free guide for any hazardous gas, whether that be a toxic gas or a combustible gas. And you will get your exposure limit values there. You'll get the molecular properties of that gas. You'll get anything that you need to know about that particular gas, whether it's toxic or combustible. And then here, the American Conference of Governmental and Industrial Hygienists, a couple of different things that they look at here when it comes to threshold value limits. There are going to be certain occupations where staff are going to be exposed to hazardous gases. Think about someone who works in a vehicle repair shop, right? There are going to be fumes in that facility. And this organization looks at that and says, okay, what are the different threshold value limits that we need to consider? And the first one there is time-weighted average. Over the course of a normal 8-hour workday or 40-hour work week, what is an acceptable level of gas exposure, of toxic gas exposure, right? Is it 1 ppm? Is it 2, right? These are the types of recommendations that this organization makes. Then you've got the short-term exposure limit, which would be the maximum concentration to which a worker may be exposed to. And then the ceiling is a concentration that shall not be exceeded during any part of the working day. So that ceiling that you cannot go above. So I wanted to just talk a little bit about some of the critical environment alarm suggested set points. And one of the reasons I bring this up at this point of the conversation is, those organizations make recommendations for alarm levels and set point levels, and we take that information and we publish that information in our Introduction to Gas Detection, our study guide. That I will actually forward out after the call. I'll send out an email to all the attendees, and I'll put a link that you can download this study guide. But this here on the screen here is a snippet of that study guide. And this talks about our suggested gas alarm set points based on those regulatory authorities, okay? So when we think about gas detection, we've got our sensor transmitter. These sensor transmitters are able to pick up different levels of gases and then take appropriate actions based on those set point levels. So if we look at this, this chart here, we've got our suggested alarm set points. Let's take the fourth one down, carbon monoxide, right? That's a very common gas that we monitor for vehicle exhaust. Now we can see the sensor type here, which is electrochemical. We can see the mounting height, which is what's the height where we're going to mount that in the facility. In this case, it's the breathing zone, right? That's the area where you've got considerations for human health and safety. That's where humans are going to breathe in that air that we need to monitor. Then we've got the coverage area of that sensor. Every sensor has a coverage area that we need to consider. And then we've got a standard range of ppm, okay? Now, those next three columns there, you can see low alarm, mid alarm, and high alarm, right? And we've got different ppm levels. So for carbon monoxide, again, the fourth one down, the low alarm set point is 25 ppm. So in that case, we may be looking at a parking garage application, and we say, okay, if that P2, parking level 2, has a gas sensor level of 25 parts per million of carbon monoxide, let's turn those fans on to low, right? We've got spilled up. There's probably a car idling. Let's turn the fans on to low. All of a sudden, that ppm reading jumps up to 50. Now we've got a midpoint alarm, set point alarm, 50 ppm. Now we're starting to get a little bit higher. Maybe we've got 4 or 5 cars idling there. Maybe we need to turn those fans on to high. And then high alarm, 100 ppm, right? 100 parts per million of CO. Now we're starting to get into the danger zone. So now we might want to tell the system, hey, let's send a message over the DDC system to say that we've got a high alarm for carbon monoxide. We may want to trigger an audio-visual horn strobe to alert people in that area that we've got a high concentration of carbon monoxide. Maybe there's an issue with the fan, right? Maybe that fan is not turning on or it's not running. Right? Just to, I won't go through all these, obviously, but if we look at the bottom section there, the bottom gas there, nitrogen dioxide. I usually ask if the room, when I'm doing this presentation in person, does everyone know the difference between carbon monoxide, CO, and nitrogen dioxide, NO2, in the context of vehicle exhaust? I'll give you the answer. Carbon monoxide is incomplete combustion of gasoline. NO2, nitrogen dioxide, is incomplete combustion of diesel, which is why we have a dual sensor transmitter. One transmitter, we can monitor CO, carbon monoxide, and NO2, nitrogen dioxide in the same transmitter. Okay, it's called a dual sensor transmitter. And you can see, look at the bottom there. You've got your type of sensor, you've got the mounting height, the breathing zone. It's that same breathing zone, 4 to 6 feet above the finished floor. Coverage area, very similar, 5,000 square feet. And now we've got our standard range of ppm, 0 to 10. And look at these last 3 columns again. Again, the bottom gas, nitrogen dioxide. Low alarm is 0.7 ppm, 0.7, right? Mid alarm is 1 ppm. High alarm is 1.5 ppm. So what does that tell us about the toxicity of incomplete combustion of diesel compared to incomplete combustion of gasoline? Far more toxic, right? Far more toxic. So again, we can measure both of those gases, carbon monoxide, nitrogen dioxide, in one transmitter. In some jurisdictions, we also monitor propane, which is a combustible. And in other warehouse applications, we might want to measure and detect hydrogen for battery-powered fork trucks, which is the off gas there would be hydrogen. Okay, so we've talked a little bit about the types of hazardous gases already. Just want to talk a little bit more about that quickly. Toxic gases typically measured in ppm, parts per million, sometimes ppb, which is parts per billion. We can get that specific. We've already talked about CO and NO2. Ammonia is another one. Ammonia used for chillers, for ice making machines, ice rinks, curling rinks, and other applications. Very toxic gas. Matter of fact, there's 3 people that lost their lives as a result of ammonia overexposure in British Columbia about 8 years ago, right? Very toxic gas. Chlorine, another very toxic gas. When you say chlorine, a lot of people would say, yeah, that's for swimming pools. It's not necessarily what you might think. We're not necessarily monitoring the chloramine levels within the pool, the public area of the pool. What we're considering there for chlorine is monitoring that mechanical room where that chlorine is stored, because if there's a leak of that chlorine in a small space, it could be a very, very toxic. And of course, chlorine for waste water treatment plants, very common application. Chlorine, for those of you who know, is also a very corrosive gas. So instead of just putting in a standard sensor transmitter, like this one here, which is a NEMA 4 enclosure, a lot of engineers will specify explosion-proof sensors, not because it's a classified area, but because we don't want the inside, the electronics of that to be corroded by the high concentrations of chlorine in that room. Combustible gases, these are measured percentage LEL. That stands for lower explosive limit. Sometimes you'll see that referred to as LFL, percentage LFL, which is lower flammable limit. Some of the gases here are methane, propane, hydrogen, and now, of course, with these new A2L refrigerants, we could add refrigerants to this category as well because they do have a flammability component to them. And when we get into refrigerants, historically, we've always measured refrigerants from a ppm standpoint for their toxicity, right? You can see some of the refrigerants listed there, R22, R123. These are legacy refrigerants. And then down below, you'll see A2L refrigerants, which, again, less harmful to the environment if they escape out, but do have a small flammability component to them as well. So from a gas detection standpoint, we are now being asked to measure these leaks from a percentage LEL, from a combustibility standpoint, okay? And there are some implications to that when it comes to the type of sensor. And I'll get into that a little bit when we talk about the sensors themselves. Asphyxiants, what we're talking about here is percentage volume of oxygen in the air, right? So what's the typical percentage of oxygen in the air in your building or outside? It's about 21%, right? 20.8, I think. And we can measure both a high level of oxygen, which could lead to combustibility, as well as a low level of oxygen, which could lead to asphyxiation. And one of the applications here that I find quite interesting, you'll see this a lot of times in laboratories where an early warning sign of a gas leak would be the depletion of oxygen. Another application is in MRI rooms. So within North America, Every MRI room requires an oxygen depletion system. And the reason for that is that MRI room is circular. It's got a magnet that is spinning around inside of that MRI room at a high rate of speed. That generates heat, okay? And that heat from that spinning series of magnets is cooled by a helium-based refrigerant, okay? Now, if we think about helium, think about when you were a kid, or who knows, maybe last week, you took a helium balloon and you sucked in the air and your voice changes, but it's not going to kill you, right? But in medium and high levels, what a helium-based refrigerant will do is it will actually displace the oxygen in that room. So what we do in that particular application is instead of having our sensor right inside the MRI room, because we can't do that because it's got electronics inside and metal, and the MRI would probably suck the electronics right out of closure. We take a larger unit, which is similar to this guy here. We call it our CGAS SD, our sample drop. And we've got a nipple here and polytube going in and sampling that air within that room. The main controller would live outside of the Faraday cage, which is that MRI room, okay? So that we can continue monitoring those oxygen levels and making sure they're at a safe level. If they do get down below, I think it's 19.5 is a low alarm, we can then trip alarms and messages to DDC systems and so on. The last two categories there, TVOCs and particulates. Volatile organic compounds, we can see measured in ppm. We do some of that. This tends to get a little bit into that indoor air quality space, but we do have a number of sensors for this as well. Probably the most common application for particulate monitoring would be smoke, right? With the forest fires over the last number of years, we see a number of engineers specifying smoke particulate matter monitoring for indoor spaces. Right now, we're working with our dealer in the California area. It's actually an Apple head office or one of the regional head offices where they want to monitor particulates, smoke, in their facility. And when the particulate levels gets to a high enough level, they can take the appropriate action when it comes to that filtration of that air and maybe recirculation of that air inside the facility as well. So here's a little synopsis here of the applications that we've been talking about a little bit. You can see starting at the bottom, you've got your parking garage, a multi-level parking garage, hotel rooms. We're starting to see some hotel rooms specify refrigerant monitors in every room where they're utilizing VRF systems, right? For those VRF systems where you get a leak, you've got the explosive potential, even though it's low, and the fire marshal say, "Hey, we need to monitor those VRF system in hotel rooms," right? Warehouses we talked a little bit about. You've got vehicles entering inside. What about the lift trucks, right? The forklifts, how are they powered? Are they propane powered? Are they vented batteries? That's going to impact also if we need propane or hydrogen monitoring as well. Indoor swimming pools with the chlorine we talked about. Greenhouses, CO2 enrichment, right? We can monitor those CO2 canisters themselves as well as the CO2 levels inside of the greenhouse for those optimal growing conditions. Schools, chillers and boilers, of course. In some cases, natural gas monitoring in the laboratories and VRF units as well. Wineries and breweries have certain off gases from ethanol to CO2 and so on. And ice arenas, a number of different applications there. We talked a little bit about ammonia already. CO2 in the playing area. And then that Zamboni or the ice cleaning machine. How is that machine powered? Is it gasoline? Is it propane? Is it diesel? Is it the battery powered? That's another consideration that we can do. And in that application, we've got 3 different types of gases that we're monitoring, all of which, we'll talk about this in a little bit, can be monitored through our main control panel. You only need one control panel to monitor multiple gases and multiple zones within a facility. Like I said, we'll talk about that in a little bit. So gas sensors themselves, hopefully you can see this. This is a gas sensor itself. And this is a solid state sensor. It's an NO2 sensor. And this detects the presence of gas in the air. And inside of this unit, you have like almost like a gel-like or a jam-like consistency inside there. You've got a membrane at the top of it, and that allows the air to come through. That mixes with that electrolyte that's inside, and with through microwatts sends a signal into this plug-and-play sensor, which then sends that signal over to our sensor transmitter, which then sends that signal over to the main controller to take the appropriate action, whether it be fans, connection to DDC system, output to a fire alarm system, whatever the case may be, right? This is the gas sensor transmitter here. And again, we can connect up to 128 of these to the flexible control system as well. Different types of gas sensors for different types of gases. You can see here that we've got electrochemical sensors for toxic gases like ammonia, chlorine, and oxygen. A different type of sensors required for our combustibles, which is a catalytic bead. For TVOCs, we've got the PID sensors, photoionization type for TVOCs. And then at the bottom there, you can see the refrigerants, a couple of different type of sensors for refrigerant monitoring. Okay, and I'm going to talk a little bit about that because within the industry, what we've seen over the last few years is that when it comes to monitoring of refrigerants, if you think about a typical chiller room where you've got a couple of chillers in there, you know, there can be other you know, off gases or other gases that are present in that room. If you think about maybe paints or solvents, you know, that are inside of that room, maybe some cleaning products, they can in fact cross-contaminate or poison a solid-state sensor. And we have seen a number of instances of that, and not just our company, within the gas detection industry. And that's why we have made the strong recommendation for when we are monitoring refrigerants that we utilize an infrared sensor. So instead of the sensor having like an electrolyte inside, it's got a series of mirrors and light refractions where it is able to very specifically look for that specific target of refrigerant, whether it be R454B, R410A. And it's not as susceptible to cross-contamination or poisoning. It's going to last about 2 to 3 times as long. You can get up to 15 years with an infrared sensor. In addition to that, your calibration frequency, it's only required every couple of years, okay? It doesn't have the same issues with drifting like a standard solid-state sensor would, right? So again, for refrigerants, we would make a very strong recommendation that we utilize an infrared sensor for those. The only downside, I guess, that you could say when it comes to infrared sensors is that they're more expensive, right? But again, if you think of what the purpose of this gas detection system is, yes, it's for the protection of life and property, but it also has to have the confidence of the building managers, right? If we put a solid state sensor in there and we start getting false alarms or incorrect readings as a result of cross-contamination or poisoning, that is going to lead to a lack of confidence in the system, and that's not where we want to be when it comes to gas detection. So again, for refrigerants, again, strong recommendation towards the infrared sensor. So all sensors have a shelf life. Of course, the solid state sensors more so than the infrareds, of course. But if you think about this sensor, I mentioned earlier, it's like an electrolyte inside. If we keep this sensor on the shelf for 10 to 12 months, the insides will dry out a little bit to the point where you will not be able to calibrate that sensor, right? So by virtue of this sensor being plugged in to the unit, we have the ability to it heats up and it will extend the life of the system. Lifespan, sensors don't last forever. They've got some environmental exposures may impact their lifespan. If you look at high exposure of gases, if it's exposed to a really high level of gas, they will impact the lifespan of that sensor. Heat as well And when I mean heat, I mean a blast from a weed whacker. If you do that, will impact the life of the sensor as well. And then calibration frequency, right? Sensors should be calibrated regularly, and our recommendation is every 6 to 12 months. That's going to depend on the type of sensor as well. Your standard sensor every 12 months, oxygen sensors every 6 months, and like I said, infrared sensors can be every 12 months, or sorry, every 2 years. How it works. Just a quick stop here. Can everyone still hear me? I know my Teams window popped off my screen. Just want to make sure everyone can still hear me. Okay.
You're doing great. I think you just
Awesome.
needed a break to take a sip of water. That's why you asked the question. No,
Yes, perfect. You read right through me. Yes, thank you so much. All right, here's how it works. Okay, so we've got our gas sensors out in the field. We've got our main controller, which is our FCS here, the main controller. Think of that as a similar to an FACP, a fire alarm control panel. This unit does not sense gas within itself. You need your remote sensors on it. This little section here is in fact an audible alarm. And then we can take the appropriate action and activate external devices, whether they be exhaust fans, connection to a BAS, a DDC system, connection to audible and visual alarms, and in some cases, external monitoring through analog outputs from the gas detection system to perhaps a supervisory input to a fire panel. So another way of looking at this is in this depiction here, right? You've got a vehicle that pulls in, and for whatever reason, maybe they're talking to their boss or their spouse, they've got the car that's running, and that gas is picked up by our gas detector. That sends that signal over to the flexible control system that, with a series of relays, sends a signal over to the fans, whether that be green heck or whatever the case may be. And for a high alarm, we've got an output to a horn strobe. And right there, you've got yourself a standalone gas detection system. It's just working in the background, connecting to the fans and the horns and strobes. However, we can take an output from our flexible control system via BACnet, MSTP, to the control system of the building and or connection into the fire alarm control panel. Could be an analog output to a supervisory input. And in that case, we could call the fire department to take the appropriate action in the case of a high alarm. Okay. So I'll just stop there just quickly. And for those technologists in the room, we'll talk a little bit about how this system communicates. Like I said earlier, this C-gas sensor transmitter, again, we can have two sensors built inside of this, CO and NO2 in the case of vehicle exhaust. We can connect up to 128 of these systems to our flexible control system, okay? The wiring between your C-gas gas sensors out in the field and your FCS control panel is daisy chain, and it's a 4-conductor, 16 or 18 gauge cable, okay? 2 of those conductors are for power, powered by a 24-volt DC power supply within the flexible control system. And 2 of those conductors are for communication. In this case, the native communication between our sensor transmitters and our flexible control system is Modbus. Okay, so we've got Modbus communication. We've got standard wiring length considerations. Once you go over, around 4,000 feet, we need to consider adding some additional power supplies and also adding a network extender for that Modbus communication to make sure that signal is strong enough to get back. And again, this is digital communication, right? Digital Modbus communication. So therefore, the wiring can be in daisy chain. One device to the next to the next. We address these sensors, and via Modbus, the main controller knows exactly what zone or what sensor that alarm is coming from. It's not like the old analog systems where you've got a star configuration and you've got individual inputs into the panel, right? That's an analog system. This is digital, so we can zone out the system. So if you look at the screen there, we've got a parking garage. Well, let's say you have a 6-level parking garage, right? Again, the system is smart enough to know that, look, we've got a high alarm level on sensor number 146. 146 is linked to P5. And if we have a high concentration of gases in P5, we only need to turn on the fans in P5, not for the rest of the parking garage. And that's what we mean by zoning of the system. Okay. Now, if we have a DDC or a BAS system inside that facility, we can take a backnet out from this flexible control system into the DDC system and bring all that data into that DDC system for logging, tracking, or whatever the case may be, okay? There is another way to do that as well. These individual sensor transmitters are field configurable, which means we can configure them to communicate via Modbus, which is the native communication, or we can select BACnet. So we can have this individual sensor live on a third-party DDC system, okay, and have it communicate via BACnet to that third-party DDC system and have that system turn on the fans as well. I would say that's a less common design. You know, a lot of engineers will look at it and say, look, this is a life safety system. We don't want to have one manufacturer sensing the gas and another manufacturer or another system turning on those fans, right? What if there's a problem? Did the sensor not pick it up? Did the DDC system not turn on the fans properly? Was there a problem, some problem with communication? So typically what we'll see is you've got your sensor transmitter, flexible control system that turns on the fans. And if you need that data out, well, take that via BACnet out of the system controller. Okay. I will also pause very, very briefly and just highlight our I say newer, not brand new. We'd spent out for about a year and a half, our CGAS SC, our self-contained gas sensor. This guy here does both the sensing of the gas and the controlling of the fans. Okay, so if you take the previous iteration, our smaller sensor and our main controller, if you blend those two together, you'll get the CGAS SC, which is a self-contained gas detector. Senses those gases and also has those relays built into it for turning on those fans, including VFDs as well. This guy here, you could also add a third sensor. So it's got the two sensors built in. You could add a third sensor like hydrogen or methane or propane or a refrigerant and have it a fully self-contained 3-gas system. Very cost effective when you're working on those smaller applications, right? Say you're working on a fire hall, very popular for fire hall. Maybe it's a police station. Maybe it's a small vehicle repair shop where you just need 1 or 2 sensing locations. This is a great option for that, right? Very cost effective. The only consideration is, in addition to running power, you also need to run your fan relay wire directly into this unit as well. It's not a centralized panel. You're running your fan relay wire into this unit directly out in the field. Okay, specification considerations. There's a number of things that we need to think about when specifying gas detection systems. Regulatory compliance. What are the code requirements? Do we need to monitor a CO and NO2? Do we need to monitor propane? Swimming pools? Do we need to monitor chlorine? That's a very important thing. What's the code requirement? The type of gas, right? What are the specific gases and concentration levels? Again, using our study guide, we can use this as a guide to figure out what are those concentration levels and set point levels that we need to be concerned about. Sensor technology, right? Why would we use an infrared sensor over a solid state sensor, right? In a refrigerant application, what would be the best sensor for that application? Environment and location. What are some of the things we need to consider? Are we doing a fire hall where we've got washdowns and we need to be concerned with water maybe getting inside of the sensor? In that case, we could put a splash guard over top, which allows the air to come in from the bottom, but prevents water from getting inside of that particular unit. And then integration and compatibility, right? How do we want our gas system to connect with the rest of the building? Is it a standalone gas detection system with a simple turning on of the fans and maybe turning on strobes in a high alarm situation? Or do we want to have it connect to the building DDC system with data going back and forth, right? That's certainly a consideration that we want to think about. What's my time here? I've got almost 1:45. Okay, so coverage area. Every sensor has a coverage area that we need to be concerned with. So we've got here overlaid a series of gas sensors. In this case, we've got 5 sensors. And you can see the yellow in the middle of those circles. That is the sensor itself. And those circles around, that is that area that one sensor can cover, okay? So in the case of vehicle exhaust, we use approximately 50-foot radius, which means take your sensor, go 50 feet out, draw a big circle around it, and that's your area of coverage, okay? You will see a little bit of overlap from time to time. We really need to make sure, due to the way the parking garage is configured, that we're covering every square meter of that parking garage. So that's why you will see some overlap. Again, this could be zoned out. We could have this 5 of these sensors on P1, 5 on P2, 5 on P3, and so on, and all connected to one flexible control system. One of the other considerations too is you will see wherever possible, we try to get these sensors toward the center of the parking garage on columns. We took this sensor and installed this up against a wall, right? Against a long wall. Of course, we're reducing the efficiency or effectiveness of that sensor by 50% because we've only got 180 degrees of coverage. Whereas if we take the sensor, we put that in towards the center of the parking garage in a column, we've got full 360-degree coverage for that sensor. Mounting heights, you know, your typical toxic gases are going to be in that breathing zone, right? That's where it presents that that serious impact for humans in the breathing zone, 4 to 6 feet above the finished floor. We talked about the lighter than air gases. We need to consider putting those up high. Heavier than air gases down towards 6 to 12 inches above the finished floor. One of the considerations, again, when we're putting them either down below or particularly up high, think about where we're putting these sensors. They need to be calibrated as well. So we need to be able to get a scissor lift or a boom lift up to service those sensors. Applications and solutions, you know, again, we could spend a whole other hour going through all of these applications. You can see here the parking garages, warehouses, chiller rooms, and boiler rooms are our most common applications. And then down below, you'll see some of these other applications as well. Again, I could go into some of these applications here and talk a lot about it, but we don't have time for that. So with that, that's my presentation from the PowerPoint. I'm going to just briefly go into our website quickly here, just to confirm. Can everyone still see the website here?
Yes.
Perfect. This is our website. I'm sure a lot of people, when doing presentations, say, "Oh, our website is great," but our website is actually great. It's a really good website. We only do gas detection. We don't make actuators. We don't make PPE or jet engines. We're only making and manufacturing gas detection systems. So you can get all the information you want regarding our gas sensors and detectors. You can go to our controllers. These are the 2 controllers we just talked about. You can get all the information on those applications that we talked about right here by simply clicking on the application. It's got your key considerations. It's got your target gas, in this case, which is oxygen deficiency. It's got a little printout here, or a little magazine article on why we want to monitor these gases. And down below, it's got the product associated with that particular application, right? Very, very simple. But one of the areas in the website I really wanted to draw your attention to, particularly for those engineers on the call, is our technical library. All right. We go down to the support, hit our technical library here. You will see by application a number of different documents for these different applications. So we've got our engineering specifications. And here we've got vehicle exhaust, refrigeration chiller rooms, boiler rooms, etc. Let's stick with vehicle exhaust briefly here. And now we can see we've got control schematics for vehicle exhaust central panel. Again, central panel, that's going to be our FCS. And that document is available in PDF, CAD, and a Word. So let's just click on that just to give you an example. Open that up. And there we go. You can take this information. Here we've got our flexible control system. To the right, we've got our two C-gas transmitters. Again, you go up to 128 of those. We've got our remote power supplies, horn strobes. We've got additional relay modules to fan starters. We've got analog outputs. And we've got at the top there, BACnet MSTP to the BAS system. Down below, you'll see vehicle exhaust for carbon monoxide and nitrogen dioxide. All of the part numbers listed there. It's all done for you. Here's your sequence of operations, right? Low alarm, detection of 25 ppm or 0.7 ppm NO2 shall activate exhaust fans, makeup air units, and louvers. High alarm, detection of 100 ppm, shall activate horn strobe. And then your system notes, right? You've got your mounting heights, you've got your radius of coverage, you've got the wiring, you've got your communication type, you've got the specific type of wire, and you've got your power. So all of that information is available to you. I'll show you one more. If we were to take vehicle exhaust standalone units, again, what we're talking about here is our C-Gas SC. They're self-contained. Very simple, right? A lot more simple than the last one. Remember, this does the sensing of the gases as well as turns on the fans. So we've got our C-Gas SC here. We've got two optional analog outputs, two relay fans to starter, or two relays to fan starter, our horn strobe, and then BACnet to the DDC system. Part numbers, same sequence of operation, and your system notes. It's all there. So again, lots of more things that we could look at. There's other schedules here as well that we could look at that give you all that information as well. So lots of information here that you can utilize. I would really encourage everyone on the call to take a look at our website, and you can get all that information that you need. Let's just go back to the presentation briefly.
Hey, Jeff, do you have,
Yes.
Is there a link to the study guide? Did you talk about that at all?
Oh, yeah, good point. This study guide, I referenced it earlier.
Yeah, I've got, you can't see it, but yeah, I've got that on my desk. It's pretty handy. I know a lot of people don't use paper anymore, but it's got some good stuff in it.
Exactly. So when I follow up from this call, I'm going to put a link in that email that I sent out for the follow-up, and we'll get that out to everyone. I'm going to put myself on the spot here. If I go to the website and just simply type in study guide, let's see if it brings it up. Study guide. Oh, there it is right there. Study guide, PDF. Let's download that. And there's our study guide, right? So I will send this out in the link as well. And thanks, Scott, for bringing that up. Yeah, absolutely. I will.
Yeah, it's just got a couple of nice references about, parts per million of things to watch out for, and the spaces and the chemicals, just, really quickly looking at it.
Yes, absolutely. Absolutely. So yeah, thanks for that. So I'm gonna wrap up here. Again, I will send out a link for an email with links to all the things that we've talked about here. We have a dedicated email address for any inquiries, which is sales@cetci.com, that we will send out to everyone. And really, would recommend take advantage of that. If you have any questions about gas detection, please send that over to us. You will see in some mechanical drawings that there's actually not a lot of detail when it comes to the gas detection on a lot of the projects that we work on. We've got apps engineers that are able to work with you and your teams, whether you're an engineer to get a manufacturer's recommendation, or as a contractor to lay out those sensors and to give you a bill of materials. We will do full submittal docs as well. In addition to that, we will do full shop drawings for our projects that we get involved with, okay? One last thing. we can fully pre-program this panel as well in our shop if we have a full sequence of operations and fan schedule. So we make that installation very, very simple when it comes to the contractors and the boots on the ground. So with that, that's my story, and I'm sticking to it. I'm open to any questions that anyone might have.
Yeah, typically, what we see on a product like this is, we don't expect our consultants and customers to know all this. And if you're working on a project, something really simple like a multifamily with a parking garage, and you want to get started on a gas detection system, we'd ask you some questions, but when hopefully you have some plans, and we would send it off to CET. We wouldn't make the selections ourselves. And then with sending them plans, they can help locate the sensors, and they can send it back to us, and we can start building a job. That's typically what happens on these.
Absolutely.
And like you mentioned, some of these become kind of an afterthought on the design side, right? There'll be a small sequence of parts per million or controlling the fans. But in terms of the details, the layout, the locations, a lot of times it falls on the contractor. But if you're an engineer and you're specifying, this is one more way to make your project go smoothly and ensure that the contractor is going to give you what you need for that building. So I know Jeff's presented to one of my engineers for me, and they loved it, and they're going to start dropping those details on all their future parking garages because they said it gave them more security about what they were providing to the owner. We do have one question in the chat from Martin. How are A2L sensors calibrated, and are there issues getting R454B for testing? This came up on a California job recently.
Yeah. So R454B, of course, is one of the common A2L gases that we've got sensors for. So and I believe you can get standard cal gas, calibration gas for the 454 gas. If you can't, let us know and we can help you source that. When it comes to calibrating, I think I mentioned earlier in the presentation that the calibration frequency, we only recommend every couple of years because that sensor is not going to drift quite as much. It's really just a matter of making sure that sensor is still working, maybe just a cleaning of that sensor as well. It does get a little bit of a buildup of dust, and just making sure that sensor is in fact still functioning and reading, but again, will not drift to the same extent as a solid state sensor. Does that answer your question? Oh, you're on mute. You're...
Well, we'll let Martin know, and if Martin, if you need more detail on that, feel free to reach out to me, and we can have a separate question with Jeff and go into more detail, maybe this specific project. And we'd love to take a look at it. If you need some assistance with that particular project, send it off to Dorse, and they can send it to us, and we can help you with that design. Absolutely, yes. So, okay. Excellent. If you have anything, please, Jeff said he's going to send out an email with his contact information. At Dorse, we'd always like you to reach out to us because hopefully we're also doing your fans on the project, and we can coordinate getting the proper fan selections, the proper gas detection system, and control sequences set up, all in one nice little package for you. So if there are no more,
Jeff,
questions,
didn't we set up a specific wiring diagram or something with Fairgreen motors?
Did we set it up?
No, I remember you and Robert talking about that.
Oh, yeah. I mean, we've got our sometimes sample wiring diagrams are enough for the engineer to get started, and then we'll do the custom wiring diagrams after. We've done a number of them for Robert and your team. Yes. Yep. So perfect. Well, thanks a lot, everyone. Really appreciate your time, and thanks, Chris, for setting this up, and look forward to any further correspondence as a result of this presentation. So thank you.